to this point, we've been talking about non-electrolytes. So now we're going to talk about the electrolytes. Strong electrolytes, remember, are things that ionize completely when they're put into solution. And they will affect the freezing point and boiling point and the osmotic pressure more because they separate into ions, meaning there are more particles for the given concentration. So the Van 't Hoff factor, which is symbolized with an italic I, is the ratio of moles of particles in the solution to moles of formula units dissolved. So this would be what we could consider the concentration of the solution. Like if it's 0.2 moles per liter sodium chloride, then you would, in a liter, you would expect 0.2 moles, but the moles of particles would be greater because those, the compound is going to separate. So actual Van 't Hoff factors are not exactly equal to the expected values because some ions effectively pair up even when they're in solution. And so this is a picture of that. So here we've got, sodium ions and chloride ions, and they're surrounded by water molecules, that ion dipole force, and they're moving around. But even though they're like coated in water molecules, they still kind of see each other and kind of like each other. And so you do get some of these ions kind of hanging around together. Then they're acting as one particle instead of two. So here's a table. These are looking at 0.05 molal solutions. So for a non-electrolyte, the Van 't Hoff factor is just 1. For sodium chloride, we would expect it to be 2, right, because there are 2 ions in sodium chloride. The actual measured one is 1.9. Magnesium sulfate, that has 2 ions, magnesium and sulfate, and so we would expect it to be 2. It's actually only 1.3. Magnesium chloride, there's 1 magnesium and 2 chloride ions. So we expect it to be 3. The actual value is a little bit less. K2SO4, again, we've got 3 ions there. And FeCl3, there's 4 ions, 3 chlorides and 1 iron. So the expected Van 't Hoff factor is 4. The measured is only 3.4. So the measured Van 't Hoff factors, if you need to use those, they will give them to you. Don't try to memorize those. Most of the time, we can just use the expected Van 't Hoff factor, which we can figure out by looking at how many ions are in one formula unit of that compound. So we can add this to all of those other equations. So the freezing point depression is the Van 't Hoff factor times molality times freezing point depression constant. And the boiling point elevation, same thing. And for the osmotic pressure, again, we're just multiplying it by the Van 't Hoff factor. Okay, so this is the kind of question they like to ask on exams. Which aqueous solution has the highest boiling point? So what causes the boiling point to be higher? More particles, right? And notice these are all aqueous solutions, right? So the solvent is water. So that's the same for all of them. And looking at this, the concentrations are the same. The concentrations of molecules or formula units. But then you have to look at, well, what would the Van 't Hoff factor be for these? C2H222O11. That's carbon, hydrogen, oxygen. That's a molecular compound, right? We recognize ionic compounds as starting with a metal or starting with NH3. This is none of those. So then the Van Hoff factor that we would expect here is 1. It's not going to make any ions. What would we expect for NaCl? 2. Because there's 2 ions, sodium and chloride. How about for magnesium chloride? 3. So when you look at the change in boiling point, it's going to be the Van Hoff factor times the molality times the boiling point elevation constant. So the molality for these things are the same. The freezing point depression constant is the same. So the thing that has the most particles will have the highest boiling point. Does that make sense? And a question like this is typically how they test you on colligative properties. Sometimes they'll give them to you like this, where the concentrations are all the same. Sometimes the concentrations will be a little bit different. So, like if I said, well, this is 1 molar C12H22O11. Well, that's 1 particle and a concentration of 1. This is 2 particles and a concentration of 0.5. So these should have the same effect, right? But this one's still bigger. Okay. Calculate the freezing point of an aqueous 0.10 molal FeCl3 solution using a Van Hoff factor of 3.2. So the freezing point depression is the Van Hoff factor times the molality times the freezing point depression constant. So this is I, and this is M, and Kf. Is it 1.82 or 1.86? 86. So you would have to go look that up on an exam. It would be given to you, or you'd be given a place to look it up. So the Van Hoff factor is 3.2. The molality is 0.10. And the freezing point depression constant, 1.86. So we end up with units of degrees Celsius. So this is telling me 0.5952. It's kind of a bad 0. It's kind of a bad 9. 5952 degrees Celsius. The change in the freezing point, right? How do we figure out what the actual freezing point is? We're going to have to subtract this from 0, right? And again, it's a lot easier to think about if you draw or even just imagine a thermometer, right? So here's the normal freezing point for water. This is the change. Freezing points go down, boiling points go up. They move away from each other. So this is going to go down, so it's going to be negative 0.5952. 2 sig figs, so negative 0.60 degrees Celsius. Any questions? So strong electrolytes will also have a larger effect on vapor pressure lowering. So when you're calculating the vapor pressure for a strong electrolyte solution, you need to take that into account when you're calculating the mole fraction. So let's do that here. A solution contains 0.115 moles H2O and an unknown number of moles of sodium chloride. The vapor pressure of the solution is at 30 degrees is 25.7 torr. The vapor pressure of pure water is at 30 degrees is 31.8 torr. Calculate the number of moles of sodium chloride in the solution. So there were actually two different equations. Let's just go back there real quick. Okay. So this is Raoult's law. The vapor pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. Or the lowering of the vapor pressure is equal to the mole fraction of the solute times the pure solvent vapor pressure. Since we're trying to find out something about the solute, this equation is going to be easier to use. We could still use that one, but this one might be easier. Or actually, would it? Let me think. So if we're looking at the mole fraction of the solute, we're going to have moles of sodium chloride over moles of sodium chloride plus moles of water. If we look at mole fraction of solvent, we're going to have moles of H2O over moles of NaCl plus H2O. Yeah, I was wrong. So if we use this one, the variable we're looking for is moles of sodium chloride. We're only going to have one thing we're solving for here, x. If we use this one, we're going to have two x's in our equation, and we're going to have to combine terms, and that's going to be a little bit messier. So I reversed my decision, and we want to use this one. Okay. So the vapor pressure of the solution is equal to the mole fraction of the solvent times the mole fraction of the pure, I'm sorry, not the mole fraction, the vapor pressure of the pure solvent. So here our solvent is water. So the vapor pressure of pure water was given to us as 31.8 torr. The vapor pressure of the solution was given to us as 25.7 torr. And so with those values, we can calculate the mole fraction of solvent. So the mole fraction of the solvent, well, let's just call it H2O because that's what it is. The mole fraction of H2O will equal the partial pressure or the vapor pressure of the solution divided by the vapor pressure of water. So I took this equation and I divided by the vapor pressure of the pure solvent to get the mole fraction. So that's going to be 25.7 torr divided by 31.8 torr. The torrs are going to cancel out. .80818. remember, mole fraction should always be between 0 and 1. So that's the mole fraction of water, which equals the moles of water divided by the moles of water plus the moles of sodium chloride. So we have the moles of water, 0.115. This is where we need to be careful, because the vapor pressure, does it depend on the number of moles of sodium chloride or the number of particles formed by the sodium chloride? Particles formed. So this isn't really going to be moles of sodium chloride, it's going to be moles of ions, right? So let's rename that moles of ions. So the moles of H2O was given as 0.115. So down here we've got 0.115 moles plus, let's call it Y, because there's a chi on the page. So cross multiply this. Get rid of the fractions. Then here we have to use the distributive property. We have to distribute this to both of these. So we've got 0.80818 times 0.115. 0.09240. Plus 0.80818 times y is equal to 0.115. And then we have to subtract the 0.0924 from 0.115. .022 0.60. So now we're going to take this value and divide by that value. Get 27296. I didn't plan my workout very well. So if we have this many moles of ions, how many moles of sodium chloride do we have? Well, we could write it out using dimensional analysis, right? We could say, okay, well, I'm going to multiply by 1 mole of sodium chloride is going to give me 2 moles of ions. Because it can be hard. It's like, am I supposed to multiply by 2 or divide by 2, right? Well, for every 1 mole of sodium chloride, you get 2 moles of ions, and then you don't have to think about it. You have to divide by 2. And I'm going to round to 3 figs, 0.0136. That one is a little bit tricky, but that's the kind of a trick you should expect, possibly on my exam or on the ACS final. Let's see if I got it right. 0.014. Let's see what I did. When I did the subtracting, well, wait. Anyway, it's a sig fig thing we don't really care about at this point. Any questions?
So we don't just multiply I in the initial.
Yeah, you can't just put I in there because this isn't the concentration of the solute. It's the mole fraction, right? And so the mole fraction is going to have, I guess you could think of it this way. Let's do this in a different color. You could think of your mole fraction of water as being the moles of water divided by the moles of water plus I times the moles of NaCl. You could do it that way. That would work also. But it's not as simple as just throwing an I in there like the other ones. Yeah. Any other questions?
For that Bancroft, that I factor,
Mhm.
it was like the expected and what we assumed is that difference. Did magnitude of the ion charges have anything to do with it, or is it just all common?
Yeah, so what causes or why is the amount of difference larger in some than others?
In that table, I would see it too, like that change in
Yeah.
the difference seemed a little bit bigger on some that had a higher.
That's a good question.
I was just wondering.
Yeah. Off the top of my head, I don't have a real quick answer for that. But you might be onto something, because here the charges are +1 and -1, and here we have +2 and -2, and there's a bigger difference, right? So here this is +2 and 2 -1s. This is 2 +1s and a -2, and those are about the same. And then here we have a +3 and 3 -1s. So I would guess it does have something to do with the magnitude of the charges on the ions. It's a great observation. Most of the time, you would just use the expected factor. So as I mentioned earlier, the osmotic pressure of solutions administered as intravenous fluids is critical. So a hyperosmotic solution, also known as hypertonic, this is more osmosis. It's going to have a larger osmotic pressure than the bodily fluids. So it's going to be more concentrated. And it's going to pull water out of the cells. So this is what a normal red blood cell looks like. It's kind of a donut shape. That's not a hole in the middle, but it's an indentation. So if you take the normal red blood cells and you put them into a hyperosmotic solution where the pressure of solutes outside is higher, then you're going to be pulling water out of the red blood cells. And this is called crenation. when that happens. Hypoosmotic means it's a lower concentration. It has a lower osmotic pressure than what's inside the cells. And so that's going to cause the red blood cells to pull water in. And if it keeps going, they're going to burst, right? So this is just my hypothesis. But, having 5 boys, the girl made some bloody things too. But, there's been a lot of bleeding at my house, and it got on things, right? So I've gotten pretty good at getting blood out of clothing. Never murdered anyone, though. But what works really well to get blood out is just cold water. Just let it soak in cold water. And I kind of think part of why that works is that causes the blood cells to burst. That's my theory. Any questions? The reason they talk about osmotic pressure instead of concentration, right, is, well, for one thing, in the cells, it's not really practical to measure the concentration because there's lots of different things dissolved in the cellular fluid. But you can measure the osmotic pressure. In fact, you could find if it's equal just by putting red blood cells in the solution, and if they stay the same shape, that's the same osmotic pressure, right? And then the solution that you're giving the patient, it might have sugar in it, which is a non-electrolyte, and it probably has sodium chloride, which is an electrolyte, so that's going to form ions. And it maybe have some other things that are going to form ions. And bottom line, what you care about is this going to pull water out or push water into the cells? And osmotic pressure measures that, regardless of the complexity of the solution. Any questions?
Is that why we would get finger pricked a lot?
No, I think they were doing something else when they were pricking your fingers.
Or just something I instantly thought of.
Yeah.
That would make sense too.
Oops. So hypoosmotic or hypotonic will pump water into the cells, causing them to swell or burst. And what you want is isoosmotic or isotonic fluids. So isotonic saline is 0.9 grams of sodium chloride per 100 mils of solution, which would be equivalent to a 0.9% mass to volume concentration. So why would they use grams over milliliters? Because it's easy to measure. Okay, so if you're going to make an isotonic saline solution, I'm going to measure out 0.9 grams of sodium chloride, and I'm going to put it in a flask, and I'm going to add water until I get to 100 milliliters, right? Instead of trying to weigh the solution as I add water, that's trickier. And measuring the volume of solid sodium chloride doesn't make any sense. So that's why sometimes there's a mass volume percent. Often it's mass or volume. But that's a common unit in medicine, percent mass to volume, and mass of solute per volume of solution. All these different units exist because they are convenient for different purposes.